All right, so we just finished up part of the notes on 12.4, which were tangent and normal vectors. And we talked about capital T, which is the unit tangent vector, and capital N, the principal unit normal vector, and we had drawn them in here. So we're just going to wrap up these notes. It shouldn't take very long, so that's where we're going to get started. If you have a moment, read the comic. It's fantastic. It's from my favorite webcomic, which is called xkcd.com. If you've never been there, you should absolutely go there. The guy who writes it is actually a previous NASA roboticist, and then he quit that to become a full-time webcomic, and it's phenomenal. Most of his comics are about math, science, computer science, engineering, and they're just absolutely spectacular. He also has 2 books out. You're going to think I'm like getting paid to plug for him, but they're amazing. One of the books is called What If, and he explores questions like how fast would you have to throw a baseball to get it to exit the Earth's atmosphere? That was interesting. The most interesting chapter in What If is he said, what if you wanted to make an actual periodic table of the elements by stacking all of the elements on top of each other? And he explains very clearly why that could never work, because basically the world would explode. So it's exceptional. You should totally read What If. And my favorite Christmas present this year was a book called Thing Explainer, and I'm just going to tell you to Google it because it's phenomenal. So anyways, XKCD, you should totally go there. I've spent a minute and a half plugging for the guy, but he's awesome and worth looking into. All right, so last but not least here, I want to talk about this last thing, which is acceleration and tangent and normal components of acceleration, just because we've talked about projectile motion, and this is kind of where Calc 3 really thrives, is using calculus to model realistic things. And there's a lot of things that are modeled using calculus, but motion is the most accessible for most of us. So anyways, if you have r of t, and that's your position vector, and n of t exists, then the acceleration a lies in the plane determined by t and n. So basically what it's saying is your acceleration vector will always lie in the same plane as your tangent vector, your like principal tangent vector, and your principal unit normal vector. And acceleration isn't just like a primary thing. There's actually different components of acceleration, and this part I kind of found interesting. So there's something called the tangential and normal components of acceleration. So if r of t is the position vector for a smooth curve C, for which n exists, then the tangential and normal components of acceleration are as follows. The tangential component of acceleration is the derivative of speed. In other words, the tangential component is a magnitude. It's a number, and it's the derivative of the speed, which is a square root, which is an expression. You can also get that by doing a dot t, where a is the second derivative of r. And you can also get that by doing v dot a over the magnitude of v, so v dot a over speed. Then there's the normal component of acceleration, and that's called the centripetal component of acceleration, because that one you can see right down here, that's the one that points inward. Your centripetal force is the thing that pulls you inward. Like as you're turning your car around a bend, it's going to tip toward the turn. It doesn't tip away from the turn as you're driving. So that's kind of what we're looking at there. So we have, where am I going here? We have our tangential component, which is here. We have our normal component, which is there. And again, these are components, so these are scalar values. And we're just going to go through and kind of use the formula, because I feel like I'm talking way too much about it and not just doing it. So let's, just do it. So I'm going to come down here and say, all right, here's a nice curve. Here's a nice pictorial representation. If this is r, so this guy right here, if this is r, a, your acceleration vector, comes inward like that, and that acceleration vector has a tangential component, which is your acceleration within the path that you're traveling, and a normal component, which is that guy, and t and n, there we go, are unit vectors, so a dot n is the length of this. A dot t is going to give you the length of that, and then together they make A. This is actually kind of part of a projection, if you remember that from a little while ago. If you don't worry about it, but that's kind of where these come from. Again, though, I'm talking, let's just do. So find the tangential and normal components of acceleration for this guy. Okay, fine. So r of t is given by 3t negative t squared. So then v of t is your derivative, 3 negative 1 2t. And then a of t is 0, 0, 2. So if I want the tangential component of acceleration, I can do v dot a over the magnitude of v. And that's kind of where I like to go with it. These other ones are fine, but then I'd actually have to calculate t and n. And if I don't already have them, I really don't want to calculate them. So I'm going to use this formula and say a sub t is going to be v dot a over the square root of 3 squared plus 1 squared plus 2t squared over the magnitude of v. So the tangential component of acceleration is going to be 4t over the square root of 10 plus 4t squared. Okay, sure, fine, whatever. Now, the normal component of acceleration, you can actually just get using this square root thing. Well, where did that come from? That I explained quite clearly. It's because this makes a right triangle. I can say, well, if my acceleration vector is right here, and my tangential component of acceleration is this guy, then the normal component is just really the third side of a right triangle. So it would be a squared minus a sub t squared equals a sub n squared, which is where that formula comes from. It's just Pythagorean theorem. So a sub n is going to be the square root of the magnitude of a squared, which is really just going to be 2 squared, minus a sub t squared, which is this guy. And so a sub n, so that should be a capital N, is going to be the square root of 4 minus 16t squared over 10 plus 4t squared. And I am just going to leave it like that. And basically what you can do from there is plug in values for t, and it'll tell you your acceleration as you're driving in a certain direction, and your acceleration that's pulling you inward using that centripetal force. All right, well, that's it. This was under 10 minutes. I just wanted to make this into 2 videos. You're going to do the problem set, see how it goes, and ask me questions in the forum if you need to. That is all. So our joke for today is, what should you do if you find a dinosaur in your bed? You should sleep in another bed. I know, that one's really terrible. I should give you a better one. Let's see, the better one is going to be, why can't your nose be 12 inches long? Because then it would be a foot. I know, that one's terrible too, but it's a little bit funnier than the dinosaur joke.